Students, in this video, I am going to go through two examples with you guys where I am going to talk about the graphical relationship between a function and its inverse. Okay, so let's take a look. So what I have right now on the screen is a line, and I'm calling this line f of x, and f of x is defined to be 2x plus 1. So just really try to get comfortable in expressing an equation as a function. And again, just like in the last video, what this is saying is if I input some quantity of x, I am going to get an output of f. Okay. The example that we're looking at, unlike the examples that we saw in the last video, there were some context to it, right? It was like a conversion between temperature units or a conversion between time and temperature. In this case here, there's really no context involved. However, we can still perform much of the same kind of skills. You may be wondering, like, why do I want to perform on those skills on things that have no context? Well, that's because what we're doing here is we're practicing and analyzing these abstract situations so that we can then apply it to more pragmatic situations. Okay, so the more we understand about functions and the more we understand about this idea of an inverse, okay, the more we can see it in real life situations. So right now, this equation here, I can express it as a function notation, or I may express it as an equation such as y is equal to 2x plus 1, which we all are super familiar with. Okay, so I'm actually going to write out the inverse equation in two different notations for you guys to see. Okay, so the first one here is I have not y, but actually, yeah, I'll do this. So I have y is equal to 2x plus 1. What we can do, okay, to find the inverse, just like in the last video, we're going to try to isolate x. So to isolate x, we're going to subtract 1 from both sides. And then finally divide by 2. So I end up with x is equal to y minus 1 over 2. And you may say, like, oh, we're done, right? That's the end of the problem. Not quite, because this problem has no real context, okay? The way in which we write out the inverse function is by doing this. We replace x and y with y and x. So wherever we see x, we write y, and wherever we see y, we replace it with x. This replacement doesn't have to happen at the end. You could have done this in the very, very beginning, okay? But either way, okay, the x and y's, okay, will have to be reversed. And why do we reverse it? Well, that's because we've done a reversal, right? That was the whole idea behind what an inverse was. So now the dependent became the independent, and then the independent became the dependent. Okay, so this is the inverse function of my original equation there. And there's another notation that you should be familiar with, and that is you can also write out, because f of x is equal to 2x plus 1, another way of writing this is with this notation. So don't confuse this negative 1 with being an exponent. It is not an exponent. That negative 1 there, okay, is telling the reader that this is the inverse of f, okay? So whatever input we throw in here, okay, what we're going to get as a result, okay, is going to be the x-coordinate of the original function, okay? And whatever x value that we throw in there is going to be the y-coordinate of the function, okay? So again, the x and y's, right, they're in reverse, okay? What was the original input became the output. Let's try to graph this out, okay? So I have f inverse of x is equal to x minus 1 over 2. So this is, in fact, the inverse function here, okay? What I want to do with this is I am going to, I recognize that this is a linear equation, and I know that m is equal to 1/2 and b is equal to -1/2. So because m is equal to 1/2 and b is equal to -1/2, okay, I can then plot out what this line looks like. I know that y is equal to 1/2 there, and So then I can graph out the line for it to look like this. And almost there. I'm trying to get it as perfect as I can, which sounds crazy, but okay. So this is the inverse function right here, and this is f inverse of x is equal to x minus 1 over 2. So the goal of this video is to find out geometrical graphical relationship between the inverse and the original. Can you take a look at how are these two things related, right? If you're thinking like, oh, wait a minute, isn't the red line the mirror reflection of the other? And you're absolutely right. It's actually the mirror reflection of the black over the line y equals x. So all the points, okay, if you look at this, this point over here, which I'm going to call 0, 1, okay, it, when reflected over the line y equals x, is going to be over here. It's 1, 0. This point over here, which was 1, 3, is now over here, and it's 3, 1. So anywhere, okay, on this line, if I call this a comma b, the reflection of that will be on the other side, and it will be b comma a, right? That's what we had studied in geometry, right? When we reflect something over y equals x, the x's and y's get reversed. Okay, so that's really interesting. Something else, when we flip this, okay, and it may not necessarily be as obvious right now, but something happens with the domain and range, okay, because the x and y's, okay, gets reversed. The x's becomes the y's in the inverse, and then the y's in the original becomes the dependent, okay, in the inverse function, okay. So the domain, what happens is the domain of f, those are all the x coordinates, right? Those are all the x values that we throw into f of x. They become the range for f inverse of x. And then the range of f of x, they become the domain. Again, this is just a fancy way of saying that the x's and y's, they get flipped, they get reversed. This is not as apparent, or the significance of this is not as apparent in this example right here, although it will be more apparent when the domain and range are not both all real numbers. If you look at this right now, right, the domain for f of x here, okay, the domain for f of x is all real numbers. We can substitute anything we'd like inside of f, and that would be okay. The range, same thing. Whatever x value we throw in, okay, we're going to get back some y coordinate, and the line stretches to positive infinity and negative infinity. This is also going to be all real numbers. As it turns out, it's going to be the same for the inverse, right? So it's not as obvious, or the significance of that last piece of fact I gave you, but it will become more apparent in the next example, okay, which we're going to take a look at right now. Okay, so one more time, just to summarize, the in this one example, we went over again some of the notations, okay, to writing out the inverse function. Again, we reverse the x and y's, okay, and we isolate y again, right? actually, that's not what we did first. We isolated x, and then we reversed x and y's. So that process could have been, done in reverse. All right. So let's take a look at the next example here. I have the square root function. Okay. So right now, let's talk about what the domain and range is for this guy. So the domain, okay, is x is greater than or equal to -2. The range is y is greater than or equal to -1. So if this is the domain and range for the original function, okay, let's say y of x, then therefore y inverse of x, what will be the domain and range then? According to what I told you from the example above, the domain and range will be flipped, right? So the domain, what would that be? The domain would be x is greater than or equal to -1. The range is y is greater than or equal to -2. Let's see why or how, okay? So again, we're going to find out what the inverse function is. So right now I have y is equal to square root of x plus 2 minus 1. If I do what I did in the first example, and again, we could have reversed the x's and y's in the very first step, and that's what I'm going to do, is to show you there's really no difference in the order that we do things. So I'm going to switch that first. And what I'm going to do now is I'm going to attempt to isolate y. So I'm going to add 1 to both sides. And then to get the square root, to get the y plus 2 out of the square root, I'm going to square both sides. And then I'm going to subtract both sides by 2. So this becomes my inverse function. And again, you can write it like this, okay? Or, in function notation, you can write it as y inverse of x. Either one is the correct, either one is the same, okay? Again, or you can write it as y inverse of x is equal to x plus 1 squared minus 2. Either case is the same thing, okay? The notation there. All right, so let's try to graph this. Wait, don't you recognize that this inverse function is actually a quadratic equation with the vertex at -1, -2? And that's exactly it. So we're going to graph this, pinpoint this, right? And recall that the inverse function is actually the reflection over the line y equals to x, right? It is the reflection of over the line y equals to x. So actually, we could have graphed this thing out without having to come up with the equation, but we could have just actually taken these points here and reflected over the line y equals x. And I promise you we'll end up in the same place. So I take this, which will end up over here. All right. And the graph ends up looking like this. Which then you're probably wondering, wait a minute, that's not how a quadratic equation is supposed to look. And you're right. This is not how a quadratic equation is supposed to look, but this is only a partial drawing of y equal to x plus 1 squared minus 2. Why am I putting in a partial drawing only? Well, that's because the domain and range of the inverse, okay, must be the reversal of what the original function was. Okay, so again, this idea is reiterated, okay, by us drawing this parabola, but it would be incorrect of us, to draw the other half, because the other half is not a part of the inverse function. Okay, it's only this right half that I had there. So the domain and range, okay, they must correspond with the domain and range of the original function, but it's in reverse. Okay, and the graph of the inverse is the reflection of the original function over the line y equals x. Okay.